Continuing on physical chemistry, chapter 4, we're in section 7 now. Now we're going to talk about open systems and chemical potentials. Now here's a beaker, we have a solution of some sort, and notice this is an open system, so that matter can get out, matter can get in. Now first of all, let's say we have one single phase with K components. So K is the number of components. So we have the Gibbs free energy. The Gibbs free energy is going to be a function of temperature and pressure, but also the amount of substance 1, the amount of substance 2, the amount of substance 3, etc., all the way to the amount of substance K. So remember, lowercase n means the number of moles, and then subscript I means, I for the substance. 1 for substance 1, 2 for substance 2, etc. So the differential of G is going to be the partial derivative of G with respect to temperature, holding pressure, and all the substances I constant, times the differential of temperature, plus the partial derivative of the Gibbs free energy with respect to pressure, holding temperature and all the substances I constant, times the differential of pressure, plus a whole bunch of others, so we're going to just write it as a sum, from I equals 1 to K, so that means we're going to go through each K substance. We're going to have the partial derivative of Gibbs free energy with respect to the number of moles of that substance I, holding temperature and pressure, and all the other substances constant, times the differential of the amount of substance I. Now we're going to define, remember, an equal sign with 3 lines means define or always equal to. So we're going to define mu sub I. We're going to call this the chemical potential. So the chemical potential is going to be the partial derivative of the Gibbs free energy with respect to the number of moles of substance I, holding temperature, pressure, and all other substances constant. Now remember, Gibbs free energy is extensive. So that means the partial derivative of Gibbs free energy is extensive. The number of moles of substance I is extensive, therefore the partial derivative of the number of moles of substance I is extensive. But mu sub I is intensive. It is independent of the system size. Now chemical potential is the driving force behind chemical reactions. This is a chemistry class, remember. So the differential of the Gibbs free energy is minus the entropy times the differential of temperature plus volume times the differential of pressure plus the sum from substance 1 to K of the chemical potential of I times the differential of the number of moles of I. Intensive, extensive. So remember, we're always going to go from high potential to low potential. That's the direction of spontaneous change. So the differential of the internal energy, similarly, would be temperature times the differential of entropy minus pressure times the differential of volume plus the same sum. The sum from substance I1 to K of the chemical potential of substance I with respect to the number of moles of substance I. So this is the formula for open systems, but still only one phase. So the chemical potential of I is going to be equal to the partial derivative of internal energy with respect to number of the moles of I, holding entropy, volume, and the number of other substances constant. And it's also equal to the partial derivative of enthalpy with respect to the number of moles of substance I, holding entropy, pressure, and the other substances constant. And it's also going to be equal to the partial derivative of the Helmholtz free energy, holding with respect to the number of moles of I, holding volume, temperature, and the other substances constant. Now what if we have more than one phase though? Well, let's say that alpha is a general index of any phase in the system. Now remember, we had an alpha before, and alpha could be proportional to. So this is a third definition of that symbol alpha. So make sure you pay attention by context. What does this symbol mean this time? So we're going to have the differential of Gibbs free energy is equal to the sum over all the phases alpha of the differential of the Gibbs free energy for phase alpha. So this alpha is an index, and it indicates which phase we're talking about. And like I said, this is not the same alpha that we were doing back in the adiabatic calculations. This is a different alpha. So the differential of the Gibbs free energy is equal to minus the sum over the phases alpha of entropy of alpha times the differential of temperature plus the sum over all the phases alpha of volume in that phase alpha times the differential of pressure plus the sum over all the phases alpha and the sum of the over all the different substances I of the chemical potential of I in phase alpha times the differential of the number of moles of substance I in phase alpha. So we're defining the chemical potential of substance I in phase alpha as the partial derivative of the Gibbs free energy in phase alpha with respect to the number of moles I in phase alpha, holding temperature, pressure, and holding all the other substances in that phase constant. Now remember, the sum of all the phase alpha of the entropy in alpha is going to be just the entropy, because the entropy is extensive. Likewise, the sum over the phase alpha of the volume of every in alpha, all the different phases, is going to be just the total volume, and that's because volume is extensive. So now we have the differential of the Gibbs free energy is going to be minus the entropy times the differential of temperature plus volume times the differential of pressure plus the sum over all the phases alpha and the sum of all the substances I to K is going to of the chemical potential I in phase alpha times the differential of the number of moles of substance I in phase alpha. We're going to call this equation 1 so we can refer back to it. Now this equation here is true when you have multiple phases, multiple substances, and it's even true if it's reversible or irreversible. Now let's talk about equilibrium, material equilibrium. So if we have constant pressure, that means the differential of pressure is equal to 0. If we have constant temperature, that means the differential of temperature is equal to 0. Let's say we have a closed system. If we have the differential of Gibbs free energy, that's equal to 0 at equilibrium. So let's say we have the differential of Gibbs free energy is equal to minus the entropy times the differential of temperature plus volume times the differential of pressure plus the sum over all the phases alpha and the sum over all the substances, K substances, of the chemical potential of substance I in phase alpha times the differential of the number of moles of substance I in phase alpha. So we're going to get, again, this is for material equilibrium, 0 is equal to 0 plus all this. So that means this is equal to 0. So what we can say then is at material equilibrium only, well, not only, but at material equilibrium we know that the sum over all the substances alpha and the sum over the substances I is equal to the chemical potential I of phase alpha and the times the differential of the number of moles of substance I in phase alpha is equal to 0. Now remember, this is at material equilibrium. We assumed constant temperature and pressure to do this. We assumed the only work is pressure volume work, and this would also work if you're at constant volume also. Now let's compare phase equilibrium with reaction equilibrium. Let's say we have one phase with I substances. Then the Gibbs free energy is going to be a function of temperature, pressure, the number of moles of substance 1, the number of moles of substance 2, the number of moles of substance 3, all the way up to the number of moles of substance K, if you have K substances. So we can say that the chemical potential is also a function of temperature, pressure, the number of moles of substance 1, the number of moles of substance 2, etc., all the way to the number of moles of substance K, assuming we have K substances. Now, the chemical potential of substance I, remember, we defined as the partial derivative of the Gibbs free energy with respect to the number of moles of substance I, holding temperature, pressure constant, and all other substances constant. Now let's say we have just one phase and one component. Then the chemical potential of that substance I is just the partial derivative of the Gibbs free energy with respect to the number of moles of that substance I, holding temperature and pressure. And you'll notice that's just the molar Gibbs free energy for substance I. But that's only true for a pure substance. And this is only for G. It's not equal to Helmholtz energy or anything like that. This here is called the molar free energy. So what we can say then, For a pure substance, the chemical potential I is equal to the molar Gibbs free energy of the substance I. And that's all for section 7.